Hello, welcome to Chapter 3. This will be thermodynamics with applications of the first law of thermodynamics. And to get started, let's talk about aspects of physical change. So first, we consider physical change, such as when one form of a substance changes into another form of the substance, as when ice melts to water. We'll also include changes of a particular simple kind, such as the ionization of an atom or the breaking of a bond in a molecule. The numeric value of a thermodynamic property depends on the conditions, such as the states of the substance involved, the pressure, the temperature. Chemists have therefore found it convenient to report their data for a set of standard conditions at the temperature of their choice. The standard state of a substance is the pure substance at exactly 1 bar. So remember that 1 bar equals 10 to the 5th pascals. We denote the standard state value by the superscript on the symbol for the property, as in H sub m for the standard molar enthalpy of the substance, and P for the standard pressure at 1 bar. For example, the standard state of hydrogen gas is the pure gas at 1 bar, and the standard state of solid calcium carbonate is the pure solid at 1 bar, with either the calcite or aragonite form specified. The physical state needs to be specified because we can speak of the standard state of the solid, liquid, and vapor forms of water, for instance, which are the pure solid, the pure liquid, and the pure vapor, respectively, at 1 bar in each case. In older texts, you'll likely come across a standard state defined as 1 atmosphere, which is 101,325 kilopascals, in the place of 1 bar. That's the old convention. In most cases, data for 1 atmosphere differ only a little from data from 1 bar, because they're very similar terms. You might also come across standard states defined as referencing 298.15 Kelvin. Technically, that's incorrect. Temperature is not part of the definition of a standard state. Standard states may refer to any temperature, but it should be specified. So it's possible to speak to the standard state of water vapor at, say, 100 Kelvin, or 273.15 Kelvin, or any other temperature. It is conventional, though, and this is the convention, for data to be reported at a so-called conventional temperature of 298.15 Kelvin, which we conventionally refer to as just 25 degrees Celsius. So from now on, unless specified otherwise, all data will be for that temperature. For simplicity, we'll often refer to 298.15 as 25 degrees C. So finally, a standard state need not be a stable state and need not be realizable in practice. Thus, the standard state of water vapor at 25 degrees Celsius is the vapor at 1 bar. But water vapor at that temperature and pressure would immediately condense to liquid water. So let's transition, chemistry puns, to enthalpy of phase transition. So a phase is a specific state of matter that is uniform throughout in composition and physical state. The liquid and vapor states of water are 2 of its phases. The term phase is more specific than state of matter because a substance may exist in more than one solid form, each one of which is a solid phase. Therefore, the element sulfur exists as a solid. However, as a solid, it may be found as rhombic sulfur or monoclinic sulfur. These 2 solid phases differ in the manner in which the crown-like S8 molecules stack together. No substance has more than one gaseous phase, so gas phase and gaseous state are effectively synonymous. The only substance that exists in more than one liquid phase is helium. Most substances exist in a variety of solid phases. Carbon, for instance, exists as graphite, diamond, and a variety of forms of fullerene structures. Calcium carbonate exists as calcite and aragonite. There are at least 12 forms of ice. One more was discovered in 2006. The conversion of one phase of a substance to another phase is called a phase transition. Thus, vaporization, the process of going from liquid to a gas, is a phase transition, as is a transition between solid phases, such as transition between rhombic sulfur and monoclinic sulfur. Most phase transitions are accompanied by a change in enthalpy, for the rearrangement of atoms or molecules usually requires or releases energy. Evaporation is virtually synonymous with vaporization, but commonly denotes vaporization to dryness specifically. The vaporization of a liquid, such as the conversion of liquid water to water vapor when a pool of water evaporates at 20 degrees Celsius or a kettle boils at 100 degrees Celsius, is an endothermic process where delta H is greater than 0, because heat must be supplied to bring about the change. At a molecular level, molecules are being driven apart from the grip they exert on one another, and this process requires energy. One of the body's strategies for maintaining its temperature at about 37 degrees Celsius is to use the endothermic character of the vaporization of water, because the evaporation of perspiration requires heat and withdraws it from the skin. The energy that must be supplied is heat at constant pressure per mole of molecules that are vaporized under standard conditions, that is, pure liquid at 1 bar changing to pure vapor at 1 bar, is called standard enthalpy of vaporization of that liquid and is denoted as delta vaporization H. And there's a table which shows a number of these that we'll see on the next slide. For example, 44 kilojoules of heat is required to vaporize 1 mole of liquid water at 1 bar and 25 degrees Celsius. So, the change of enthalpy of vaporization equals 44 kilojoules per mole. All enthalpies of vaporization are positive, so the sign is not normally given. Alternatively, we can report the same information by writing the thermochemical equation: liquid water transitions to gaseous water with a delta H of positive 44 kilojoules. And here's a reference table which we were referring, which gives you a number of substances, including ammonia, argon, benzene, ethanol, all the way through water, and it gives standard freezing points, standard changes of enthalpy of fusion, boiling points, and standard changes of enthalpy associated with vaporization, and these are all per molar values. So note, there are striking differences in standard enthalpies of vaporization. Although the value for water is 44 kilojoules per mole, for methane, at its boiling point, is only 8 kilojoules per mole. Even allowing for the fact that vaporization is taking place at different temperatures, the difference between the enthalpies of vaporization signifies that water molecules are held together in the bulk liquid much more tightly than methane molecules are in liquid methane. We'll see in Chapter 15 that this interaction responsible for the low volatility of water is the hydrogen bond. But I'd like to elaborate on this briefly. Because it takes energy to dissociate molecules in the liquid phase far enough apart to where they're in a gaseous state, how strongly they're interacting in that liquid phase will really determine how much energy is required to separate them. So if you have strong attractive forces like we do with water with hydrogen bonding, it's going to require substantially more thermal energy to excite them enough to separate them physically into the gas state. Water interacts with other water molecules in liquid form substantially more than methane molecules interact with methane. And if we look at, say, on figure table 3.1, and we look at ammonia, although it doesn't have the same very high heat of vaporization as water, because it has the capacity to hydrogen bond well and is also a polar compound that interacts fairly readily with itself, it also has a relatively high heat of vaporization. Now, on the other end of the spectrum, if we look at helium has incredibly low heats of vaporization and fusion, associated with it, and that's because helium is inert and doesn't significantly interact with itself. Therefore, it requires very little thermal energy to separate it. So let's look at an example of determining the enthalpy of vaporization for a liquid. In this example, ethanol, C2H5OH, is brought to boil at 1 atmosphere. When an electric current of 0.682 amperes runs from a 12-volt supply is passed for 500 seconds through a heating coil immersed in the boiling liquid, it's found that the temperature remains constant, but 4.33 grams of ethanol is vaporized. What's the enthalpy of vaporization of ethanol at its boiling point at 1 atmosphere? So the strategy for this, because the heat is supplied at constant pressure, we can identify the heat supplied, Q, with the change in enthalpy of the ethanol when it vaporizes. We need to calculate the heat supplied and the amount of ethanol molecules vaporized. Then, the enthalpy of vaporization is the heat supplied divided by the amount. The heat supplied is given by equation 2.5, which is Q equals IVT, recalling that equivalency to a joule. The amount of ethanol molecules is determined by dividing the mass of the ethanol vaporized by its molar mass. So, in the solution here, we see the energy supplied by heating is Q equals IVT, where I is 0.682 amps times voltage, 12 volts, times time in 500 seconds. And this value is the change in enthalpy of the sample. The amount of ethanol molecules of molar mass 46.07 grams per mole is as follows. We have 4.33 grams divided by 46.07 grams per mole for ethanol. And the molar enthalpy change is therefore going to be 4.35 times 10 to the fourth joules per mole. Or we could rewrite it as 43.5 kilojoules per mole. Because the pressure is 1 atmosphere, not 1 bar, the enthalpy of vaporization calculated here is not the standard value, technically. However, 1 atmosphere differs only slightly from 1 bar, so we can expect the standard enthalpy of vaporization to be very close to the value found here. Note also that the value calculated here is for the boiling point of ethanol, which is 78 degrees Celsius, or 351 Kelvin. We convey this information by writing delta H vaporization at 351 Kelvin equals 43.5 kilojoules per mole. A note on good practice, molar quantities are expressed as a quantity per mole. Distinguish them from the magnitude of a property for 1 mole of substance, which is expressed as the quantity itself. All enthalpies of transition denoted delta H transition are molar quantities inherently. The high enthalpy of vaporization of water has profound ecological consequences, for it's partly responsible for the survival of the oceans and the generally low humidity of the atmosphere. If only a small amount of heat had to be supplied to vaporize oceans, the atmosphere would be much more heavily saturated with water vapor than it is in reality. Another common phase transition is fusion, or melting, as when ice melts or water or iron becomes molten. The change in molar enthalpy that accompanies fusion under standard conditions, pure solid at 1 bar changing to pure liquid at 1 bar, is called the standard enthalpy of fusion. Change in enthalpy of fusion, or delta fusion H. Its value for water at 0 degrees Celsius is 6.01 kilojoules per mole. And all enthalpies of fusion are positive, and the sign isn't normally given and isn't required, which signifies that 6.01 kilojoules of energy is needed to melt 1 mole of water at 0 degrees Celsius and 1 bar. Notice that the enthalpy of fusion of water is much less than its enthalpy of vaporization. In vaporization, the molecules become completely separated from each other when they go from the liquid phase to the gas phase, whereas in melting, the molecules are merely loosened without separating completely, which is what we're seeing in figure 3.1. If we take a look at figure 3.1, when a solid A melts to a liquid, the molecules separate from one another only slightly allowing them to move freely about one another, but they still primarily remain in physical contact or proximal to one another. The intermolecular interactions are only reduced slightly in this transition, and there's only a small change in enthalpy associated with this transition. But when a liquid vaporizes, the molecules are separated to considerable distance, and the intermolecular forces are reduced to almost zero, which is why they can behave ideally or near ideally, and the change in enthalpy is substantially greater. So before moving on, I'd like to go back and discuss in a little elaboration on the ecological consequences associated with water having high heat of vaporization. One of the things that we see here in Alaska, particularly in Anchorage, Alaska, is a trend in fall as the temperature is dropping for it to approach rapidly towards freezing, and then it'll linger for quite a while. It'll linger in those high 30s to mid 30s without quite freezing, often for weeks. And then when it freezes solidly and stays frozen unless a warm weather pattern pushes in. Likewise, in the spring, as things appear to be about to melt, often things will warm to just below freezing and then linger. And the reason for this is because of the amount of atmospheric water dissolved in the gas phase. That gaseous water requires a substantial amount of heat to change phases, to go from the liquid phase to the solid phase. And it requires a substantial amount of heat, equal and opposite in sign, to go from the solid phase from the liquid phase into the gaseous phase. So to take our atmospheric water and cause it to freeze is a substantial commitment of energy, and it doesn't happen simultaneously. So you see this temperature change progressively, and then it stalls. And that doesn't mean heat isn't being transferred. It means that heat is being committed, instead of changing temperature, to changing the state of the matter. And one of the things I want to illustrate, I'll actually make a little space on the following slide here. The text uses a very simple enthalpy chart to denote changes in enthalpy between magnitude that we see on figure 3.2. But I'm going to draw an alternative visualization which will help us take a look at what's going on in the big picture as we move heat through a substance. So this is going to be a little rough, but on the y-axis we're going to have temperature, and on the x-axis we're going to have heat applied to the system. And what we'll see is, typically if you have a substance, let's say arbitrarily water, and we start to push heat into it, the temperature as it's heating the substance will increase linearly. And this is going to increase determined by its normal state of how much energy it takes to heat at 1 degree Celsius per gram substance. That happens until it hits the point, the temperature at which we encounter a phase transition. Once we hit that critical temperature where you get a phase transition, as we pour heat into it, the temperature doesn't change. We're adding heat, adding heat, adding heat until we've added enough thermal energy between point A and point B to cause the phase change. And once we've caused the phase change, we get a change of phase. And let's say this is a solid in the first scenario, and now we're going to have a liquid, and that liquid's going to increase in temperature as we put heat into it. And then once the liquid's been heated, in the case of water, to 100 degrees Celsius, depending on atmospheric pressure or pressure in general, we're going to hit another point, C, where we experience a substantial amount of heat, Q, being poured into that process as part of a phase transition between the liquid phase and the gas phase. And this isn't proportional because this delta between C and D along the x-axis, it would be substantially larger than A and B because it's going to take more energy to go from liquid phase to gas phase than from solid phase to liquid phase. And then once we hit that transition, it can also increase in temperature as heat's applied to it. So what you see is these flat zones where we don't get temperature change between phase transitions, but that doesn't mean heat isn't being applied, thermal energy isn't being applied to the substance and isn't essential for that phase transition. With that little elaboration out of the way, back to it. The reverse of vaporization is condensation, and the reverse of fusion, or melting, is freezing. The molar enthalpy changes are, respectively, the negative of the enthalpies of vaporization and fusion because the heat is supplied to vaporize or melt the substance is released when it condenses or freezes. It is always the case that the enthalpy change of a reverse transition is the negative of the enthalpy change of the forward transition under the same conditions of temperature and pressure, obviously. So if we're looking at the transition of solid water to liquid water, in our first example here, that's going to have a delta H of positive 6.01 kilojoules per mole. Now, water going from the liquid state to the solid state is going to have a delta H of negative 6.01 kilojoules per mole. So generally, the delta H for any forward process is going to equal the negative delta H of the reverse process. This relation follows directly from the fact that enthalpy is a state property. For enthalpy must return to the same value if a forward change is followed by a reverse, regardless of the path that follows. And we see that in figure 3.2 over to the side here. The high standard enthalpy of vaporization of water, 44 kilojoules per mole, signifying a strong endothermic process, implies that the condensation of water, negative 44 kilojoules per mole, is a strongly exothermic process. That exothermicity is the origin of the ability of steam to scald you severely because the energy is passed on to the skin. This is something that I considered until fairly recently, honestly, even though I was burned pretty badly by steam a few times as a kid. Anyone who has been knows that the burn seems to linger and linger and linger. And that's because as that steam hits your skin, it condenses. And that act of condensation from the vapor phase to the liquid phase dumps an enormous amount of thermal energy from the water molecules into your skin as part of that phase transition. So it's not just that the steam was hot, it's that it instantly put an enormous amount of thermal energy into you as part of you being exposed to it. So the direct conversion of a solid to a vapor is called sublimation, something we experience here in Alaska quite often, and we experience even more dramatically in the interior of Alaska, where we have very, very dry conditions and very, very cold conditions. The reverse process is called vapor deposition. Sublimation can be observed on a cold, frosty morning when frost vanishes as vapor without first melting. The frost itself forms by vapor deposition from cold, damp air. The vaporization of solid carbon dioxide, or dry ice, is another example of sublimation, where it goes from the solid to the gas phase without passing through the liquid phase. At no point is there a liquid carbon dioxide present as part of this evaporative process, or not evaporative, sublimation process. The standard molar enthalpy change accompanying sublimation is called the standard enthalpy of sublimation, which is denoted by this term, delta sub H. Because enthalpy is a state property, the same change in enthalpy must be obtained both in the direct conversion of solid to vapor and in the indirect conversion, in which the solid first melts to the liquid and then the liquid vaporizes. Therefore, if we look at this equation 3.2, delta H for sublimation is going to equal the delta H for fusion plus the delta H for vaporization, thanks to them being state properties. The two enthalpies that are added together must be for the same temperature, that's critical, So to get the enthalpy of sublimation of water at 0 degrees Celsius, we must add together the enthalpies of fusion and vaporization for this temperature. Adding together enthalpies of transition for different temperatures gives a meaningless result inherently. And that's why we have to be able to talk about state at different temperatures, although it's convenient to reference everything at 25 degrees Celsius. It's not necessarily plausible for a lot of the things we're interested in probing. So the result expressed by equation 3.2 is an example of a more general statement that will prove very useful time and again during our study of thermochemistry. As follows: the enthalpy change of an overall process is the sum of the enthalpy changes for the steps, observed or hypothetical, into which they may be divided. Of course, at the same temperature. Now, before moving on, let's take a look quickly at figure 3.3, and just to confirm, the enthalpy of sublimation at any given temperature is the sum of enthalpies of fusion and vaporization at that temperature. Another implication of the first law is that the enthalpy change of an overall process is the sum of the enthalpy changes for the possible hypothetical steps into which it may be divided. So, moving along to atomic and molecular change, having wrapped up phase changes. So, a group of enthalpy changes we employ quite often in the following pages are those accompanying changes to individual atoms and molecules. Among the most important of these is the standard enthalpy of ionization, which we see here. The standard molar enthalpy change accompanying the removal of an electron from a gas phase atom or ion. For example, because hydrogen gas can transition to a hydrogen cation plus an electron in gas phase, the delta H of ionization for this process is 1,312 kilojoules per mole of hydrogen gas. This is, of course, monatomic hydrogen in the gas phase, not H2 gas, which is a very different example. Because of this hydrogen gas transitioning to cation plus electron at 1,312 kilojoules, the standard enthalpy of ionization of hydrogen atoms is reported as 1,312 kilojoules per mole. This value signifies that 1,312 kilojoules of energy must be supplied as heat to ionize 1 mole of hydrogen atomic gas at 1 bar and 298.15 Kelvin. So table 3.2 is going to give values of ionization enthalpies for a number of elements. Note that all enthalpies of ionization are positive, and we'll take a look at 3.2 on a following slide. So, a quick comment: the enthalpy of ionization is closely related to, but is not identical to, ionization energy. Ionization energy corresponds to the standard ionization enthalpy at temperature equals 0. The ionization enthalpy at different temperature can be calculated from the ionization energy by using the concepts that we're going to look at in section 3.7 specifically. So, having said that, we often need to consider a succession of ionizations, such as the conversion of magnesium atoms to magnesium-1 cations, the ionization of these magnesium-1 ions to magnesium-2 ions, and so forth. The successive molar enthalpy changes are called, respectively, first ionization enthalpies and second ionization enthalpies, and so on. For magnesium, these enthalpies refer to the process. These following processes: 1. Magnesium in gas phase is ionized by losing its first electron to form magnesium-1, and this has a change in enthalpy associated with it of 738 kilojoules. Now, the second successive ionization, going from magnesium-1 gas to magnesium-2 gas plus an electron, costs 1,451 kilojoules of energy. Note that the second ionization enthalpy is larger than the first. More energy is needed to separate an electron from a positively charged ion than from a neutral atom. Note that all enthalpies of ionization refer to the ionization of the gas phase atom or ion, not to the ionization of an atom or ion in a solid. To determine that, we need to combine two or more enthalpy changes. Now, just to visualize, anytime we have successive ionizations, we're going from neutral to, say, +1. For a metal, it will have a lower energy requirement for that ionization than the second or third. Because as noted, if we have, say, magnesium and it's without charge, for it to lose an electron can be advantageous and not require that much energy. However, once we have positive charge, it's much more difficult to separate subsequent electrical charges in the forms of electrons from that positive charge, because removing this electron distant enough to physically separate it must overcome specific electrostatic attractive forces. So let's take a look at a nice example here, combining enthalpy changes. The standard enthalpy of sublimation of magnesium at 25 degrees Celsius is 148 kilojoules per mole. How much energy as heat at constant temperature and pressure must be supplied to 1 gram, or in this case 1.00 grams, of solid magnesium metal to produce a gas composed of magnesium 2 ions and electrons? So the strategy for this question, the enthalpy change for the overall process is the sum of the steps. So sublimation followed by 2 stages of ionization into which it can be divided. Then the heat required for the specified process is the product of the overall molar enthalpy change and the amount of atoms. The latter is calculated from the given mass and the molar mass of the substance. So let's take a look at what the solution looks like. The overall process is as follows. Solid magnesium is ultimately going to transition to magnesium 2 gas plus 2 electrons, also in gas phase. The thermochemical equations for these processes is the sum of the following individual separate thermochemical processes. We have the sublimation, where magnesium solid goes to magnesium gas, and this is going to be 148 kilojoules per mole, which was defined in the question. We have the first ionization, where magnesium in gas phase goes to magnesium 1 in gas phase, and that's going to cost 738. We're going to have a second ionization, which is going to cost an additional 1,451 kilojoules per mole, and this is going to sum to 2,337 kilojoules per mole of magnesium to go from the solid state to the +2 gas state. We can visualize this in figure 3.4, looking at how all of these processes sum to a single total of 2,337 kilojoules. Now, it follows that the overall enthalpy change per mole of magnesium is 2,337 kilojoules per mole. Because the molar mass of magnesium is 24.31 grams per mole, and we're dealing with 1.0 gram of magnesium, this corresponds to, if finding the number of moles of magnesium, 1 gram divided by 24.31 grams per mole. Grams cancel, then we get 1 over moles, and that gives us our molar quantity. Therefore, the energy that must be supplied as heat at constant pressure to ionize 1 gram of magnesium metal is our number of moles times our amount of energy in kilojoules per mole, and in this case, it's going to be 96.1 kilojoules. This quantity of energy is approximately the same as that needed to vaporize about 43 grams of boiling water. Fun factoid. So the reverse of ionization is electron gain, and the corresponding molar enthalpy change under standard conditions is called standard electron gain enthalpy, which is denoted by delta EGH. This quantity is closely related to the electron affinity, as we'll see in section 13-16. For example, because experiments show that, in this case, chlorine gas plus an electron can lead to the chlorine anion, chloride, delta H for this process equals negative 349 kilojoules. It follows that the electron gain enthalpy of chlorine atoms is negative 349 kilojoules per mole. Notice that electron gain by chlorine is an exothermic process, so heat is released when a chlorine atom captures an electron and forms an ion. It can be seen from table 3.3, which we'll see in 2 more slides, which lists a number of electron gain enthalpies, that some electron gains are exothermic and others are endothermic. So we need to include their sign specifically. For example, electron gain by an oxygen ion is strongly endothermic because it takes energy to push an electron onto an already negatively charged species. In this case, 844 kilojoules per mole to put the second electron on an oxygen which contains a single electron already. The final atomic and molecular process to consider at this stage is the dissociation or breaking of a chemical bond. As is the process, looking at hydrochloric acid in gas phase being divided into hydrogen and chlorine in gas phase. The corresponding standard molar enthalpy change is called bond enthalpy. So we would report the hydrogen to chlorine bond enthalpy as 431 kilojoules per mole. All bond enthalpies are positive. Some bond enthalpies are given in table 3.4. I've rattled off a few tables, and we're going to do one more slide, then we're going to go through these tables. Note that the nitrogen-nitrogen bond in molecular nitrogen, N2, is especially strong at 945 kilojoules per mole, which helps to account for the chemical inertness of nitrogen and its ability to dilute the oxygen in the atmosphere without reacting to it, because oxygen is typically pretty reactive. In contrast, fluorine-fluorine bond in molecular fluorine is relatively weak at 155 kilojoules per mole. The weakness of this bond contributes to the high reactivity of elemental fluorine. However, bond enthalpies alone don't account for reactivity because although the bond in molecular iodine is even weaker, I2 is less reactive than F2, and the bond in carbon monoxide is stronger than the bond in nitrogen gas. But CO forms many carbonyl compounds readily, unlike nitrogen gas, which is highly inert. The types and strengths of the bonds that the elements can make to other elements are additional factors. So on some level, we can rationalize the inertness of nitrogen based on its bond strength, but we can't exclusively rationalize inertness or reactivity based on bond strength. A complication when dealing with bond enthalpies is that their values depend on the molecules in which the two linked atoms occur. For instance, the total standard enthalpy change for the atomization, which is the complete dissociation into atoms, of water is gaseous water being divided to 2 hydrogens and 2 oxygens has a delta H of 927 kilojoules. This energy of atomization is not twice the oxygen to hydrogen bond enthalpy of water, even though 2 oxygen to hydrogen bonds are dissociated. There are, in fact, 2 different dissociation steps. In the first step, an OH bond is broken in the water molecule. And in the second step, the OH bond is broken in an OH radical. The sum of the two steps is the atomization of the molecule. As can be seen from this example, the OH bonds in water and HO have similar but not identical bond enthalpies. Although accurate calculations must use bond enthalpies for the molecule in question and successive fragments, when such data are not available, there's no choice but to make estimates by using mean bond enthalpies. Point that out, which are the averages of bond enthalpies over a related series of compounds, which we look at table 3.5. For example, the mean HO bond enthalpy, delta HB HO, is 463 kilojoules per mole. It's the mean of oxygen to hydrogen bond enthalpies in water and several other similar compounds, including methanol. So, although we won't always have all of the possible variations to exactly calculate the specific change in enthalpy associated with full dissociation, we can get awfully close by using similarly structured compounds as models to have a fairly accurate prediction. And we just have to be clear of the limitations of our calculations and our predictions because of that. Now, to wrap up this lecture, we have a few tables to look at. We have table 3.2, which include the first and second and occasionally higher standard enthalpies of ionization. So we have our ionization enthalpies here. 3.3, we have our electron gain enthalpies for main group elements. And you can see the trends which we discussed in both of these tables. Table 3.4 are selected bond enthalpies. And table 3.5 are mean bond enthalpies, which we can use to approximate enthalpies for non-specifically determined systems. And this is a good place to take a break. So this will be the end of the first lecture of this chapter, and we're going to pick it right up from here and wrap up in a subsequent lecture. So I'll be talking to you about that shortly.